Okay, hi everyone, and welcome to today's paper discussion session on the neural Sheaf diffusion. And so today, what we'll be covering is some latest work by Kristen Motna and Michael Brunstein's group, okay, that tries to apply quite difficult mathematics to the already difficult graph neural network structure. Okay, but actually, if you follow me through the presentation later, you will realize that this neural Sheaf diffusion is actually pretty similar to message passing networks. Okay, just the terminology used is more mathematical, more topology, algebraic topology based. But when implemented on a neural network, actually it just uses matrix multiplication. It's very similar to existing networks. And I would say that the reason why it performs so much better than the existing ones is that it allows for more flexibility in the mapping functions, in the embedding space functions. So we shall see why this is the case. And if you're interested, there's the paper, the talk, and the blog post that most of my slides are from. You can look at the links over there. All right, so what is the problem that we are trying to tackle today? So the problem is actually a very simple one. Okay, graph neural networks are used for many different use cases. Later I'll explain some of the different use cases. But for today, the main thing will be the node classification. So for node classification, what we do is basically we have different nodes. Okay, these nodes can have different ages. Okay, so normally for graphs, we call it V and E. V for vertices, E for ages. And then based on a certain set of features, this box over here is the features. Okay, based on this certain set of features, we want to classify, okay, what the node is. So in this case, there's two classes, like red is class 1 and blue maybe is class 2. So we want to classify based on like these features, and this feature matrix, you can add it up all together in this feature matrix X. Okay, where D is the dimension of your features and N is the number of nodes. So this is the standard thing. So how do we get a neural network to classify the nodes well? Like for example, to split like maybe Facebook connections into male and female, that kind of stuff. Yeah, how do we get a neural network to do it well? And traditionally, people use this thing called the graph neural network. So let's move to the next slide. So this is the slide that I took from Peter Velikovic. Okay, I quite like it. So this is the main thing. Okay, you are given a feature space X as the input, given an adjacency matrix. So the adjacency matrix is very simple. Adjacency matrix is just 1 when it's connected and 0 when it's not connected. So like, for example, if we have this node like that to this node, node 1 to node 2, maybe I just do 2 nodes, node 1 to node 2. Yeah, so node 1 is not connected to itself, but node 1 is connected to node 2, so it will look like this. So node 1 is connected to node 2, and node 2 is connected to node 1. Yeah, so this is like node 1, node 2, node 1, node 2. Yeah, in most cases for neural networks, we also add in a self connection, okay, because then you can do some form of aggregation of your node itself. So yeah, depends on how you want to view it. So you can also add in the I over here, identity matrix. So this is the structure of a graph neural network. You pass it through, okay, some function. Okay, what function? Later I'll briefly describe what are the main ones. And then after you get this latent space H, okay, and then you can keep doing this thing, this layer-wise iteration. And then eventually what you can do is, okay, so for example, for this case, today we just do node classification. You just take this latent space here, and then you perform some form of function on it to get your classification. And usually you do like some form of sigmoid, okay, if it's just binary case, or you could do some form of if you want to calculate how well it is for a certain class or multi-classes, you can do some form of softmax. Okay, so I mean, there are other cases where you use the whole graph or the link, okay, but that's not the focus for today. So traditionally, there have been a few cases of how to get this neural network to pass the message in the like different layers. So for example, convolutional, what you do is you take the message from each of the neighbors, okay, and also including the node itself. That's why we add the identity connection earlier for the adjacency matrix. So you can get all these connections, and then you can weigh them differently, okay, with certain with certain, basically this one will give you, this function here will give you the weights for each of these features. Okay, this one is basically the embedding space. So actually later when you see the shaft neural network, there's also some form of embedding space where you embed the features into an embedding layer on which you do your calculations. Okay. So convolutional, you just take the some weighted average of all your features. Attentional, other than the weighted, rather than just using a static weight, use an attentional weight that is based on the feature space of the incoming node, of the adjacent node, and the node itself. Okay, so later you'll see in the shaft neural network, the shaft is learned via attentional weights. Okay, so they also use in fact, the exact same structure as the attentional network to learn the shaft. Okay, so just a teaser here. And then lastly, you have the message passing network, which is the most general way of doing it. So instead of just doing like a scalar weight, because this attention is a scalar function, instead of just limiting it to a scalar function, we allow for even non-scalar manipulation. You can put a kernel function inside here. You can do like 2 layers of NLP. Okay, you need not just do a scalar. You can do whatever you want inside this function. Okay, and then at the end of it, okay, this function is based on this 2. Okay, basically when you do this thing, you get a message. So you get a message over here. So this message. And then based on this message, then you then perform another neural network over to accumulate all the messages that the adjacent edges have. So you accumulate the different messages here like that. So this is the most general form of graph neural network. And actually the Sheaf Laplacian does something very similar to this. Okay, so let's move on. Okay, I don't want to spend too much time on this. Okay, so one of the insights that this paper has is that the way the graph neural network processes its information is sort of like doing heat diffusion. So if you learn like in secondary school, you have a heat source, okay, and then the heat source will propagate, okay, will keep propagating as the molecules shake and so on. So each of these nodes will propagate its information outwards, and then eventually the information will be spread all the way like that. So it's somewhat like a metal being heated up. Okay, of course, if you have another heat source here, okay, you can also have another spreading of information from here. So like that, you can also spread the information like that. Okay, and at a steady state, actually all the cells, okay, would get all the information from everywhere. Okay, and essentially, okay, this is later as will be shown one of the problems. This will actually lead to the information, the feature space of all the nodes being very, very similar, okay, because you spread all the information everywhere. Okay, so the traditional graph convolutional network by Keith, KIPF, yeah, you can, he was the one of the first few who actually stated this, actually use a form of Graph Laplacian, okay, that is going to be the focus of, so the extension of this Graph Laplacian will be what the Sheaf diffusion, what do you call that, the neural sheaf network is trying to do, neural sheaf diffusion is trying to do. So this Laplacian is given as this formula here, identity minus d minus half a d minus half. Okay, actually the Laplacian, the traditional Laplacian is given by this. Laplacian equals to adjacency minus the degree matrix. Okay, so if you do like a normalized form, you can sort of normalize the A, become identity matrix, and yeah, sorry, it's the other way around, it's D minus A. Yeah, so this is the traditional graph Laplacian, and then the normalized form, you can just like maybe divide by D, you can get this form over here. Okay, so this is actually meant so that the neural network can learn better. Okay, that's what Keith mentioned. Okay, he mentioned that if you don't do this normalization, the magnitudes may be too high for backpropagation to work well. Okay, so this actually corresponds very well to a heat diffusion process. So a heat diffusion process goes like this from physics. Okay, the derivative of the heat diffusion process can be just multiplied by this negative of the Laplacian over here. Okay, so in the end, when we want to get the next state, okay, remember the next hidden state? The next hidden state that we saw earlier was the H, right? The next hidden state can be given by the sum of the current state of X, okay, minus away this rate of change over here. So this is given like this, I minus delta theta. So in the case of like a graph convolutional neural network, this is exactly the same as like when we were to do our, like when we were to take the the normalized degree, normalized adjacency matrix like this, okay, to multiply with your feature space, okay, times your weight. Okay, this GCN here is actually similar to doing a heat diffusion, one-step heat diffusion process. Okay, and the thing is, this heat diffusion process, okay, if done too long, it can lead to very similar features, okay, which is a cause for concern. Right, so later on, you will see that the neural sheaf diffusion actually generalizes this process. Okay, so that instead of just maybe doing this Laplacian, okay, this Laplacian is actually expanded, okay, to make it even more general, more flexible. And then this this normal this Laplacian that we see over here is just a special case of the generalized Laplacian proposed by the neural sheaf network, neural sheaf diffusion network. So before I move on, let's look at what the paper tries to explain. Okay, so typically in graph neural networks, it's been shown that there's some issue with this diffusion process if you do it for too long. So the first main issue is that the graph, okay, may be heterophilic. Okay, just a brief introduction to what is homophilic and heterophilic. Homophilic means that the nodes, okay, the adjacent nodes are of the same class. Okay, that means that when you mix the information of nodes with the same class, it tends to be all right, okay, because you will still get a similar kind of information. But if you mix nodes that is from a different class, like a heterophilic, you mix different nodes. Okay, what you will see is that you will have this node here mixed with another node here. You can mix different information here, and this can contaminate your node when you spread the information. Because like sometimes if this is class 2 information, if you spread it to a class 1 node, your class 1 node will be more similar to a class 2 node than it is to a class 1 node. So if you spread information when the nodes are of a different class, okay, it might lead to wrong information being spread. Okay, so this is one of the issues of graph neural networks, okay, if we do diffusion process. All right. The other issue is oversmoothing, and oversmoothing happens when you spread your information too much. Like at each hop of the neural network or each iteration, you spread to the next neighbors and the next neighbors, and then the next one will go to the next neighbors. Eventually, your information will get spread all the way across the entire neural network if you let it spread all the way. And this can lead to degradation of performance because the features will be nearly the same everywhere. Okay, so these are the two main features, and let us see what is proposed, okay, in order to help to solve or reduce the effects of these two factors on graph neural networks. So the authors try to blend in graph neural networks with algebraic topology to create a kind of new system to perform computations on. Okay, to be honest, actually the algebraic topology may be not that important because eventually you can treat it as embedding spaces. But let's just go through the topology anyway. So this topology basically comes from the topological field in mathematics. Yeah, topology space is usually required, okay, because you cannot use a geometric way of representing it. So normally, if we use this in integration, we actually use like Riemann integrals. But if you use topological space, you can actually do the other kind of integral. Can't remember what's the name of that, but basically you can do it using sets instead of using the number line. So this is the idea of the topological space. Instead of using space, we use sets to represent the space. Okay, so this set, right, in order for it to be in a topological space, okay, there's a lot of names in the mathematical literature like Hilbert space, some other space, but the idea is that this set needs to be consistent with itself. So in order to do that, you need to have the set, okay, having the empty set and the full set, okay, belonging to this subset collection of subsets. Okay, so this collection of subsets is like a proxy for the amount of space that or the amount of geometry that it is being defined on. Okay, then also any intersection and union is, okay, it will also be in the set. Okay, so this is one of the, okay, actually this two should also be in the set. So this collection of sets, okay, is basically one of the spaces here. But we don't have to go so much into detail for this because it doesn't really matter too much. What you need to know is that you have a list of sets, okay, and then you can define its union and you can define its intersection. Okay, So the idea of this topological space that they use here is really just to define spaces. And later you can see that this U, V, and this union, right? I mean, you can easier to treat it as Venn diagrams actually, because the topology is only used for the proofs. The main thing is that you can map this to a node. Okay, so what happens is this is U, and this is V. And the intersection of U and V, is the H. U intersect V. Yeah, so all these are in the same topological space because we have defined that the intersection and the unions are all in the same collection of sets. Okay, so we can define this space like that. So really the idea behind all this is so that we can use this thing called sheafs, okay, that define some way of passing information across this topological space. Okay, but in all honesty, later you will see that all this is not very needed. All right, but this one makes it very difficult to understand the paper because they suddenly bring in all this. Okay, but I just need to give this explanation here because this is the main crux of trying to like generalize graphs to use algebraic topology. All right, so how do we do neural sheaf diffusion then? So it's actually the same diffusion process we saw earlier, just that the Laplacian matrix is more complicated. There's more restrictions to the Laplacian matrix. Okay, so this is the idea of sheafs. Okay, sheafs is defined on a topological space, okay, that can actually restrict the amount of information that pass through. So you can see they call this restrict, okay, of the data of X to a smaller region U. Okay, I want you all to just probably forget about this definition. Okay, you can just treat this Fx to Fv. Okay, this is a mapping. So a mapping is just maybe a matrix multiplication. Okay, mathematically, this is the definition. Okay, mathematically, this is the restriction of data, but actually what it does is that is actually mapping. All right, so this one I think maybe it's easier if I were to just say like how this relates to traditional ways of doing GNNs. This way of mapping from like this X here as your features, this is your original, like maybe your input. And then you map to this Fx, this maybe is the embedding space or feature space. And then what we do is basically we allow this feature space, okay, to be able to transfer to another feature space. So this idea of sheafs, okay, is mathematical, but when implemented on a graph neural network, it is basically just saying that this is a function to map my input feature space to the embedding space. And then between embedding spaces, I also allow you to do a mapping between embedding spaces. Okay, I hope this is clear because this is really what I realize this whole thing is doing. Okay, the math behind it, okay, it sounds cool, but when you actually implement it, it is really just trying to find some matrix multiplication to do mapping vectors. Okay, I mean, just to demonstrate, okay, let's say this Fx here, okay, is given this vector like maybe a vector of 1, 2. Okay, so this Fx is like 1, 2. And then what we can do is when we want to do this mapping, let's call this mapping, okay, let's give it a name. I mean, there's a very complicated formula, but let's give it, okay, maybe I will just use like, wait, let me use a math symbol. Okay, let's just use this symbol. Okay, whatever this symbol is. Okay, this symbol here, okay, which maps Fx to Fv, which maps this Fx to Fv, is none other, okay, than just a matrix multiplication. Okay, so in neural networks term, when we want to implement it, this phi function can be like a d by d, where d is the feature space. So maybe in this case, if I want to do the identity function, I will just do like that. Okay, so when we do this, okay, we will get back the same vector 1, 2. Okay, so we have just defined like how to do this mapping from here to here. Okay, of course, from the original input space, X, okay, map to this mapping here, we can also use a matrix multiplication. So everything here is a matrix multiplication, okay, just to be clear about what's going on. Okay, so this restrict of data is just a mathematical term, okay, but practically it's not really that necessary to understand this. All right. So how do we do shifts on the graph? As what I said just now, there's a few ways to map. Okay, one is from the input space, okay, map to the feature space. And then from feature space, you can map to each other. All right. And so originally, if you look here, this arrow here can be the arrow of the feature vector of the original input space. Okay, this vector here is a d-dimensional vector. Okay, so this is like the embedding space. Think of it as the embedding space. Okay, or the vector space. Okay, it's also used in stuff like birds, transformers. Okay, your word is put into a n-dimensional vector, right? Yep. Jet, Evan, and y'all know about the word vectors, right? Yep.
Yep.
Yeah, so this actually is like mapping into the word vector space. Okay, then in between, like from nodes, okay, this nodes or the vertex to the edges, in between vertex to edges, okay, there's also a separate mapping function. So after you do a mapping function to the edge, you can see that the vectors shift a bit. Then you can also map like that, and the vector will shift a bit. Okay, similarly, from the blue vector over here, you can again perform a similar like word embedding kind of thing. You get this embedding here. And then when you map into this other space here, you get another embedding here. And then you map over here, you get another embedding here. Okay, so what's interesting is that when you do this Laplacian with sheaves, okay, I'll show you the equation later. Okay, it actually encourages, okay, by the nature of this sheaves in algebraic topology, okay, this is where the math comes in. It actually encourages this thing here, okay, to have similar vector directions, or to have similar vectors, in other words. So they call this agreement, okay? So this means that the adjacent nodes agree on the edge information. So they agree with like what should be represented in the edge. Okay, and both of them try to make this edge vector to be similar. Okay, this is the crux of it. So it enables you to share information through the different nodes. Okay, but the different nodes will agree because when you perform the mapping into the edge, okay, the edge vectors should agree in the long run after you do this diffusion process for a long time. Okay, so this is quite interesting because this is quite different from the normal diffusion process, which doesn't have this kind of agreement. Okay, why? Okay, why is the next slide? Okay, because okay, it's actually one more slide later, but this is the definition for sheaf. Okay, it has a vector space for, so you can treat this as an embedding space for vertex, embedding space for edge. Okay, and then a linear map to map vertex to edge. Okay, and then this vector spaces, right, or the word vector space, you know, they're called stocks, and the linear maps are known as restriction maps. Or you can treat them as mappings, like just basically vector mappings are, you know, map one vector to another. So one good thing about this is that, okay, you can actually use this to form agreement. Where's the, okay, so yeah, as I mentioned here, this actually allows it to form agreement. I think the slide is much later. So now how do we construct this this Sheaf Laplacian? Okay, so this is the Sheaf Laplacian over here. Okay, the traditional Laplacian, okay, as illustrated earlier, was this equation, right? Laplacian equals to the degree minus the adjacency matrix. So actually the Sheaf Laplacian, okay, if we were to treat the dimension as d equals to 1, okay, so each square here is actually a d by d matrix, okay, which tells you how to, okay, so a layman term is like this. If you want to map v to v, okay, what must I multiply my vector from v with? Okay, so this is the kind of equation here. So actually this is, when map v to v, this is actually the identity matrix, because like, yeah. If you want to map v to u, what must my matrix be in order to map that vector? So over here, if I want to map, okay, if I want to map my u, okay, to my z, okay, what should my transformation vector be? Okay, how should I do a matrix multiplication to map the hidden space of u into z itself? Hidden space of z into u. Okay, so if you were to think of it like that, okay, what this is actually doing is that if you were to treat x at the future time, okay, if you were to treat, so this is the delta f and this is x. So x at the future time, this is xt plus 1 equals to this Laplacian times xt. So this is x at the current time. Okay, so this is actually the same formulation as like a GCN. Okay, if you treat this thing as this thing over here is actually a GCN. Okay, and basically the d is equals to 1. Okay, what we will do is like we will take in this, okay, multiplied by this vector here, this multiplied by this vector, this multiplied by this vector, and this multiplied by this vector, okay, which will give you actually this xt plus 1, okay, which will give you the new hidden space representation for xv. Okay, because remember for xv, what we do is we take in whatever hidden space representation of u, okay, and then we map in this original value of u. So this square over here, okay, maybe let me just illustrate more clearly. This square over here, okay, tells us how to map u to v. That's all. So you take the original vector representation of u, and then you pass it through this d by d matrix, which tells you how to map u to v, and then you sum it up. Okay, then you sum up for each of them, you'll get xv itself. So xv is basically the aggregated sum, okay, of all the different nodes, okay, like all the different adjacent nodes, u, v, w, z, if they are connected, okay, you take the mapping, okay, and then you will just sum them up together. So it's like some form of aggregation together. Okay, then you can see that there's these white squares here, which actually tells us that actually there's no mapping here. So this white squares here actually means 0. So it's a total 0 matrix, which means there's no mapping at all. Okay, so this is really just telling you from the graph itself. Okay, for every cycle, okay, let's take a look at the v graph. So v here, okay, is only connected to u, right? So at every cycle, u, okay, will update its value to v, and v will update its value to itself. And this is exactly what this is doing over here. You see, it's only taking in this first square number 1. Let me just put square number 1. It's only taking this square number 1 and this square number 2, and then summing them up together in order to get you your new representation of v. Okay, so this is actually just node aggregation. If we were to treat this d by d vector as a scalar value, okay, this is basically just the same as doing this. Okay, multiplying this d minus a, okay, when we multiply lx, okay, we are essentially just basically summing up the various contributions of the different nodes together and then getting the new information on that new node itself. Okay, I mean, there's some math, okay, behind how this thing here, okay, let me just clear everything. There's some math behind how this thing here, L equals to D minus A, okay, can map over to this thing over here. Okay, I mean, if you are interested, actually, this one, I learned it from one of the videos from, I think it's called the AI Epiphany channel. So you have a few nodes here. So you have like X, maybe this is X3, this is X1, and this is X2. So your degree matrix, okay, your degree matrix in the Laplacian case, your degree matrix is given by this. Okay, so your degree matrix is given by 1, 1, 2. Okay, because X is connected to one node, X1 is connected to one node, X2 is connected to one node, X3 is connected to 2 nodes. So this is the degree matrix. And then the adjacency matrix is given by this. Okay. The adjacency matrix is given by X1 connected to X3 only, right? So it's like that, 0, 0, 1. X2 is connected to X3, so it's 0, 0, 1. And X3 is connected to X1 and X2, so it's 1, 1, 0. And then overall, when you take L minus A, okay, what will you get? You will get this matrix over here. So this one, 1, 0, minus 1. So the first row will be like that, 1, 0, minus 1. The second row will be 0, 1, minus 1. And then the last row will be minus 1, minus 1, 2. Okay, so now this is the interesting part. Okay, if we were to take this, okay, and we multiply by the original vectors, x1, x2, x3, okay, what we will do is we will basically get the updated information for all the nodes. So you just take a look at x3 over here. So x3 itself, okay, this is the new x3. x3 itself will take minus x1. Okay, so it will be the same as x3 equals to minus x1 minus x2 plus 2x3. Okay, so it is actually just a way of, all right, so this L over here like that, okay, this is just a way of updating your feature space by the, I believe actually you actually still need to take the identity minus away this thing. Yeah, so eventually what this will do is that it will basically aggregate the values of x1 and x2 into x3. Okay, so we kind of need to do the I minus Laplacian. Yeah. So if you want to do like a traditional GCN, you need to do like I minus this. So it is like the aggregation of your neighboring nodes x1, x2 into this x3 vector. Okay, actually, if you look over here like this, okay, this is actually the same. Okay, if we take away this, we make this like a identity map, you can actually see that when you sum up across all of this, so for the case of this x3, okay, because x3 is connected to x2 and x1, you actually summing up x3 minus x2, and you're summing up x3 minus x1. So can you see that if we do this, all right, if we do this, okay, this is actually the same thing as doing this, the Graph Laplacian, this one. Yeah, so essentially the Sheaf Laplacian is a more general form of the Graph Laplacian. Okay, that is because we have now this cool terms over here, this one and this one, plus this. So you have these two cool terms over here. Okay, that basically tells you, which is this gray square here, that basically tells you how to map a certain vector space to another vector space. So in the traditional Laplacian itself is all the identity mapping, and all of them have dimension 1. But in the Sheaf Laplacian, you can dictate how you map from various nodes to various nodes, or various nodes to various edge to various nodes. No, sorry, actually this is all various nodes to various nodes, because it's UV. Yeah, you can map from various nodes to various nodes. But I guess if you were to extend this Sheaf Laplacian case to do message passing with edges, you can also map nodes to edges and edges to edges nodes. Okay, but right now what you can see is that it's very general here. Okay, instead of just having an identity mapping like what we do for the normal Laplacian, this allows you to do mapping from different vector spaces or different embedding spaces of different nodes to another node and so on. So it's more expressive, and this could be the reason why it performs so well. Okay, so why is being so expressive? By the way, you all are okay with this this slide, right? Because this slide is the most important slide in the entire presentation. Jet, do you understand what I was talking about just now?
Yeah, I think so. I think I'll probably need to go back and look again.
Okay, no worries. Yeah, but the idea is that the Sheaf Laplacian is a more general form of the traditional Laplacian used in architectures like GCN. All right, so that's the main thing. And yeah, the main thing to ask ourselves is, why is this more general architecture better? Okay, that's the question that I asked myself actually. And actually I found the answer yesterday. So let's see. Okay, this is the Sheaf diffusion process. Okay, I just described to you earlier. And then in the infinite time limit, this x0 will be projected into this kernel space of delta f. Okay, this is just the math properties. All right. So what is the problem of non-zero restriction map? So if we have like symmetric and non-zero restriction maps, or the mapping spaces. So symmetric means that if, like, let's say one edge map to another edge, symmetric is actually a very interesting definition. It just means that the way you map from this U, okay, and this V, okay, the way you map from this V to E, okay, is the same way as you mapping. Sorry, the way they map from U to E is the same as the way V to E. So regardless of node position, is symmetric mapping. Okay, so if you use a scalar restriction map, or they call it restriction map, but actually, in all honesty, it is just a mapping space. So you use a symmetric restriction map, you do a non-zero, and then you do a dimensional one. Okay, this is the same as a graph Laplacian, which I described earlier. Okay, but okay, such architectures, okay, for the GCN type don't perform very well. We have mentioned that earlier that it didn't do very well for heterophilic graphs. It also didn't do very well for like oversmoothing problems. Okay, but it doesn't do that well. So how do we improve it? Okay, so one of the key things is that this D may be too little. All right, this stock itself, maybe it's better instead of just doing a scalar multiplication. Maybe it's better to do an embedding space. Maybe we should do some form of kernel. So you can think of it like a kernel multiplication. Instead of just multiplying by a scalar value, we multiply by a mapping space, and it's sort of like performing a kernel operation on your original values. Okay, and this non-zero is very important. Okay, why this non-zero is so important? Let us see. Okay, so if we have the original vector space, okay, think of the original vector space of V is here. The original vector space of U is here. All right, and then in this case, we only consider a one-dimension case. Okay, so you can see that the dimension is here. Okay, you can either go up or down. So because of the need for the Sheaf Laplacian in the steady state, okay, to agree with one another, you want this, okay, in the steady state, the yellow and the blue. So basically this V mapping into E, okay, this V mapping into E is actually given by this, okay, and this U mapping into E is given by this. I mean, they could just call it this. I mean, in all honesty, they can just define a function, you know, like omega. You could just do that. I mean, who uses this? I mean, sorry, but this is like not exactly very reader friendly. I feel. I mean, in machine learning architectures, we all are very familiar with this kind of mapping spaces. I don't know why they use sheafs, but I guess it's a way to like gel into algebraic topology. Okay, but the idea is that in the steady state, your embedding space for your edge must agree. Okay, if they don't agree, what will happen is the edge will become zero. Okay, because zero agrees with anything. Okay, so if they agree, what this means is that if originally, okay, you have a feature space that is negative, like maybe -1, and your original feature space for U is 1. Okay, if you don't allow for negative weights here, okay, if you just only allow for positive weights, what will happen is that your feature space will still be here, and your feature space will still be here. They will be polarized differently. Okay, in order for the polarization to be the same, okay, what you need is a negative weight. So if you add a negative weight over here into your edge embedding here, what you realize is that with this negative weight, both feature spaces can be the same. Okay, so this is something like the heterophilic case. Okay, think of it like this original vector V in the embedding space is so negative because it's like class 1. And this vector space is so positive because it's class 2. Okay, in the traditional GCN or GAT architecture, you are just summing up the contributions from your various nodes. Okay, but because of the way, like for example, the attentional matrix are, you only allow for positive values between 0 to 1 because of the softmax. So this thereby restricts our ability to express the hidden space of these nodes, and you are only able to like sum up the neighboring nodes. So if the neighboring nodes are very different from you, you get contaminated. Okay, you don't exactly, you won't be able to express yourself that well. Okay, this is quite an important point. So if let's say, for example, okay, think of it like this. All right, you have a blue ball here, or maybe you have a black ball here, and you have a white ball here. Okay, at each time step, the white ball and the blue ball will pass information to each other, right? Okay, if let's say you are only allowed to sum up information between yourself and the white ball, okay, what will you expect to happen? Okay, maybe Evan or Jet, you want to ask, will this black ball be less black or more black? If you sum up the contributions, sum up weighted contributions, will the black ball be more black or less black? Anyone want to answer?
Should be less, right?
Yeah, so it will be less black, correct? So similarly, because of the way the aggregation is, it normally just adds up contributions. If we were to take this white ball here, we add up the white ball like that with the black ball here. Will the white ball be more black or more white or less white? So maybe this one I answer myself. Okay, this one will be less white. So you can see that as long as there's a non-zero weight, eventually in the steady state, what will happen? In the steady state, both black and white balls will become gray balls. Okay, it will become the same color. Okay, that's because it keeps passing messages to each other, but because it's forced to accumulate the message, because the weights for like GCN, the weights for GAT are typically positive. Okay, GCN can actually have negative weights. So, I mean, if you do some manipulation to your equation, you can actually have negative weights. But the original one where you multiply by this Laplacian, the original one where you multiply by this Laplacian here, okay, the original one where you multiply by this or you multiply by I minus this, the original one is all positive weights. So okay, so there's a limitation to like what the graph neural networks can express, because it's only allowed to take in positive weights. And in this case, if you don't have these negative weights, you may not be able to like preserve the original information that your vectors have. So originally your vector is very black, very white, and it's great because that's exactly what you want to keep it as. If there are two different classes, you don't want the information from the two classes to mix together, because if the classes mix, what you will get is you will get the two balls, one black, one white, becoming gray balls. And you don't want that to happen because that will affect your node classification later. Okay, so this very important point where you allow negative restriction maps is actually, I think, one of the key reasons why this Sheaf diffusion works so well. Okay,
Can I ask a question? Yep. So like you mentioned that this is over one convolution, or the less black, less white thing. What if we have like a residual connection to the next layer? Would that, help with this problem?
Okay, so if you have a residual connection to the next layer, let me just draw it here. Yeah, I think it will help a bit. Okay, so if you have a next layer here, black and white, right? And then what you do is you also take in information from your previous layer, right? Because of the rest connection. Okay, so this is like time step 1 and time step 2. So in time step 2, rather than just updating from itself and so this is like the GCN process or the GAT process. We also add in a residual connection from the earlier layers. This is correct, right? So I would say that yes, it will help to prevent. Okay, it help to prevent it from happening too quickly. Okay, because what will happen is that if this is important, okay, this node cell will tend to go to 0. Okay, your weights will tend to go to 0. Okay, because you can get the full weights from your earlier layers. Yeah, so it is possible to use the residual connections to help to mitigate this issue. But as you know, neural networks, they don't exactly go to 0 that easily. Yeah, so there will be some contamination even if you use residual layers. Yeah, so if you do it long enough, you might actually it still affect even with residual layers, just that it affects less the mixing.
I see. Thanks.
Yeah. So yeah, this is the reason why. Okay, so having these negative weights, actually, I think this is the real reason why this Sheaf diffusion works so well. I mean, the other reason is, yes, it provides a bit more expressive ways to do a kernel mapping. And I think that is undeniably useful. But I think the most important is these negative weights. Okay, why I say so, later you see the results, you will understand why I say that. Okay, so this actually reminds me a lot. I was thinking about this yesterday. It reminds me a lot of contrastive learning. So in contrastive learning, what you do is you have similar points that you want to push together, and you want dissimilar points, you want to separate them. Okay, and usually the loss function, it is done in like a Siamese network, and then you have two input images, same or different. If it's same, you want to push them together in the representational space. If it's different, you want to push them away. So this is given by this. Like if it's the same, if it's different, if y is 1, which means it's different. Sorry, y is 1 is similar. Okay, we want to minimize the distance. Okay, but if y is if y is dissimilar, then we want to maximize okay, the margin minus b. So we want to make this at least a margin m away. So this is like the Euclidean hinge loss, okay, that is used in contrastive learning. Okay, and this sort of tries to basically group points together, group similar points together and push different points away. So let us compare and contrast, okay? Let us compare and contrast this with the previous slide. So you can see that when there's different points, okay, this one and this one are different, right? So ideally, we want this mapping to learn opposite mappings. We want this to learn opposite mappings. Okay, so it's not exactly the same as contrastive learning, because contrastive learning, this is inbuilt straight away into the structure of the loss function. Here, in order to get the opposite mappings, you need to learn this sheaf. Okay, you need to learn the right sheaf in order to get this. So the sheaf needs to give you opposite signs if the two nodes are different classes. Okay, so this is a learnable sheaf. Sorry, this is a sheaf that needs to be of this configuration. It's not as clear-cut as contrastive learning. But because of the way you have this opposite directions, it enables you to agree over here. So in the long run, the kernel agrees. And actually, I think that's the beauty of this Laplacian, is that they want all the edges to agree in the end. So I think that is useful. So how do we link this to attention and contrastive learning? So this will be the discussion question later, but I'll just mention this here first. So attention is a mechanism whereby you focus on what are similar to you. So if you look at the traditional attention architecture, let's say you have originally have like maybe these 3 nodes, and then you have 3 nodes here. So let's say, for example, this node can be like, I am John. I am John. Yeah. So when you focus on the word I, all right. So I'm going to words because it's easier. When you focus on the word I, you actually focusing more on I and focusing more on John. So what you do is when you do the key value attention here, so you take the query, okay, times the key. So in this case, this is the query, and this is the key. You take the query key, this is like a dot product, okay, and then what we do is we actually do attention. So you actually do a softmax of this. Maybe I just draw a softmax like that. Softmax of this, okay, over dimension of the vector, okay. All right, so you do this softmax, and then after that you times the value. So this is the traditional softmax equation, if I remember correctly. And this actually, you can see that. So actually this k is actually like maybe ki and vi, and you sum over all the keys I, okay. So you can see that this attentional product over here, this attentional, okay, this softmax product actually is of a value 0 to 1. Okay, so you can see that when we group together the vectors, okay, like in the GAT, you actually group together these values here. You are only allowed, let me just put here, are only allowed to sum the latent representations. You can't subtract. Okay, this is one of the key limitations behind like most of the traditional message passing, GCNs, GAT, because the architecture only allows you to sum the vector spaces. And if they are of different classes, you sum, you all become gray balls. From white balls and black balls become gray balls. So attention doesn't work so well here when you have different classes or heterophilic. So this is the reason why, okay. But in terms of word spaces, okay, you have man, women, you have king, queen, like you cluster things together. So it's actually quite good for words. But when it comes to like classification of nodes, you may not want to use an attention mechanism for that very reason that you don't allow to differentiate the classes. Okay, so this is why I mentioned as the second point here, does not allow for separation of dissimilar points. Okay, on the other hand, what I mentioned just now, the contrastive methods. Okay, the contrastive method try to increase the feature space distance of dissimilar points and reduce this. Okay, this is actually very similar to what the Sheaf diffusion is trying to do. If you learn the right sheaf, if you can polarize the 2 different nodes in a different direction, and then such that when you map to the edge is of the same value, okay, because you do one negative, one positive, okay, this actually sort of does what contrastive learning is trying to do, where you try to expand the distance between different classes and also bring together the feature space of similar classes. So for similar classes, your sheaf Okay, your sheaf should be of the same sign. So we go here. Your sheaf here should be of the same sign for similar class and of different signs for different classes. All right, so this is how the sheaf diffusion does it. So at every step, they do this Laplacian matrix multiplication. Then you take the identity minus this Laplacian, and then you times with the O vector. And then eventually this is your hidden space. Okay, you can treat this as the like 2D view of your hidden space. Maybe you use some form of PCA or LDA, you know, those kind of representational reduction of dimensionality ways to view it. You can see that the more they interact with each other, they actually can learn, okay, if you use the right sheaf, okay, that distinguish the, basically, as long as the sheaf makes the different classes, okay, of a different sign for that sheaf, okay, you can actually learn how to distinguish the classes, okay, in the long run. Okay, so different kinds of sheafs induce different diffusion processes. Okay, and then in order to do node classification well, you just need to find the right sheaf to diffuse. And that is the most important thing of this whole thing. Because if you can find the right sheaf, it's easier said than done, right? If you find the right sheaf, actually, you know, finding the right sheaf means what? It means you already know which classes are separate from each other. Because to get the right sheaf, you need to sort of match the signs of the sheaf such that the two different mappings must be different signs when it's different, same sign when it's the same. Okay, I mean, of course, different and same sign is only for the d equals to 1 case. If you have a higher dimension, you have to do the same kind of thing. You need to deconflict between the different classes. So if you can find the right sheaf to actually do the diffusion process on, essentially you have already done node classification. So this is kind of like the kind of thing. I mean, if you can find the right sheaf, of course you can do the classification. But what this paper does is that it manages to say that, okay, I can learn the right sheaf. So how do we learn this sheaf? Okay, we can learn this sheaf through a parametric function phi. Okay, and this phi is given by this. So what happens is that you have this RD times 2. Okay, what this is doing is that actually you have this FV. Let's call this maybe we call this I don't know, the hidden space. Maybe we call this HV, the hidden space of V, and we call this the hidden space of U. So like the traditional graph attentional network, what we can do is we can do a softmax. Okay, HV concatenate with HU. Okay. All right. Then this thing here, what you can do is you can multiply by an attentional vector. Okay. So then this will tell you like how much to focus on for like, so for every V and U, okay, we have a unique way of doing this parametric function. Okay, so we can actually learn from VU and UV. This can be different. Okay, VU, UV, we can just like interchange these two here if we want to get the different if we want to get a different phi. So what we can do is we can learn how to map this phi, okay, as a function of my d by 2, because this individual dimension is d. Each of these have dimension d. And then what we want to do is we want to find, okay, we want to map this 2d into a d by d, which is basically the original d by d square that we saw earlier in the Sheaf Laplacian. We have a d by d square. We want to map this into the d by d square. Okay, and how do we do this? If we do this mapping, okay, initially if we do an attentional mapping, okay, what you will get is you will get a scalar value. Okay, you will get a scalar. So, okay, as you already would have guessed, how do you convert this scalar to a matrix? Okay, it's actually not that difficult. Okay, what they did is they just repeat this process d by d times. Okay, so you have different attentional matrices for each of the. So if in essence you are trying to do attention for each of these little squares here in your Sheaf Laplacian, you are trying to find out exactly what this value should be. Okay, so this is quite I would say it's quite a smart way of doing it, because you are trying to learn the sheaf, okay, from just the immediate neighbors x here v and u. From there you apply attention, you can get your Laplacian matrix. So it's very similar to get, but instead of scalars, you output your matrices. So wow, this is actually quite mind-blowing. I never thought you could do this. Yeah, but apparently it works pretty well. So yeah, let's see how they did this. And what happens? So they actually did this experiment, okay, where they actually have this thing called the bipartite graph, all right, where bipartite graph means that every node is heterophilic. So if you know what's a bipartite graph, it looks like this, okay, where so these nodes are all of class 1 and these nodes are all of class 2. And then what they do is basically they ensure that none of the class 1 connects to each other. So they ensure that the graph is very heterophilic. Okay, you always, all your nodes connect to a different class because of this bipartite graph here. So that's a smart way of constructing heterophily and trying to make sure that the traditional GNNs are doomed. Because if you mix the class, you know, black ball and white ball, it become gray ball. Yeah, so all become gray balls in the end. Yeah. So how do we then see whether this Sheaf Laplacian works? Okay, we use the worst possible case. Okay, this kind of bipartite graph to test it. Okay, and then what they found out in general is that originally the Sheaf unlearned, the train accuracy and test accuracy is quite bad. Okay, but after the Sheaf is learned, okay, the train accuracy improves and actually it doesn't go down. And the test accuracy also improves. It doesn't really go down. I mean, here looks like it go down a bit. I'm not too sure whether it goes down further, but at least based on the first few time steps, it looks like it's going up. Okay, so what you see is that the Sheaf generally improves training and tests, and diffusion time only increases the accuracy. So it kind of solves the oversmoothing problem, I hope, because they didn't show what happens for T diffusion greater than 10. I'm not too sure whether this, because it really looks like just an extension of GCN. So I'm not sure whether this, I mean, if you do T equals to infinity, whether it will still work or not. I have a feeling that it might not work also. Okay, so we have to implement this and test out ourselves, but I have a feeling that it may not just go all the way up. Okay, and then you can see that the learn transport maps. So what is a transport map? Okay, very confusing, right? At first they say restriction map, now they say transport map. Okay, so actually this is just a mapping space. So you map from one node to another node. Initially, okay, before training, all the transport maps, all the mapping spaces are all very close to 0. Okay, but after that, what happens? Take a look. What happens? Can anyone tell me what happens to the transport map? Are they more positive or more negative? You want to answer? Anyone? What happens to the embedding space, the mapping? Negative. Yes, correct. More negative. And you know the reason why it needs to be negative? Okay, I think you all should know by now. Why is this in the long run negative? Anyone can tell me why is the transport map or the embedding space negative? Okay, think of the bipartite graph. Okay, are the nodes, are the edges connected to the same kind of class or different classes? Okay, and the answer is nodes are connected to different classes. So in order to ensure that the mapping is preserved, you need to learn negative mappings. Okay. Yeah, so I would say it may not just be like negative mappings. Actually, you need one mapping to be negative, one mapping to be positive. Yeah, but over here it seems like everything negative. So yeah, I mean, it could be the case that some of this not so negative weights are actually for like one part, and then this negative weights for the other part of the graph. I mean, it could be that case, but it's not too clear why there's no like positive, because right, for your map, your U and your V, okay, you want to learn both maps, right? So you want this thing to be like maybe negative, this map here to be negative, and you want your other map here to be positive. Okay, so I'm not too sure why there's no real positive here, but at least because of these negative weights here, you can actually see that it sort of solves the problem a bit. Okay, so this is not perfect. As you can see, the oracle, okay, if you give the right sheaf to it, okay, which is like +1 and -1, you give the right sheaf, it performs very well. Okay, so it hasn't really reached there yet. Maybe there's a limitation with the attention process to learn the Laplacian. Okay, so this might be room for future work. Okay, but at least the inclusion of negative weights already showed a much better performance, okay, in order to solve heterophily. So let's take a look at how traditional methods solve like these few data sets. So I want you to just focus on this homophily level, which means like how much of the nodes are the same class. Okay, the lower, the lesser the nodes of the same class. And you can see that using a different way, so like diagonal matrix, orthogonal matrix, and no restriction for your Sheaf Laplacian, you can see that actually diagonal is actually one of the fastest because you restrict it, you can only do a certain kind of, you can only have diagonal terms. Yeah, so this actually makes it much faster in compute time, and also it gives pretty good performance. Okay, blue is actually red is the top, blue is the second, and this purple is the third performance. So you can see that especially in the heterophilic case, the Sheaf neural diffusion or neural Sheaf diffusion kind of rocks, right? It kind of does very good performance. Okay, but for all the homophilic data sets, okay, like Cora, actually Cora is like the data set that doesn't differentiate that much, because I think the feature space already, you don't even need to do graph. You see, your MLP is good enough already. Yeah, so Cora is not exactly a very good test. Okay, maybe you look at PubMed or Sightseer. Sightseer also not a very good test. It's all about the same. You look at, so maybe you look at PubMed. So for this kind of cases, you can see that actually it performs still not too bad, this neural Sheaf diffusion. Because as long as the Sheaf it learns are all like, in general, quite positive, like similar to the GCN, it should do quite well. I just want to point you to this general GCN, okay, GGCN. This GGCN actually also works pretty well. See, it doesn't look that much different. I mean, if anything, it might just be hyperparameter tuning to compare with this. So this GCN, okay, the main thing that it did, okay, it normalizes the degree. Okay, that's one thing. But the main thing that this GGCN did was that it actually allowed for negative weights. And how it allowed for negative weights, it actually used this cosine similarity to find out the weights. So this is actually like how I put it. This is like an attention mechanism, but from -1 to 1. Yeah. So it's quite interesting. Okay, because I don't quite like cosine similarity, but it's quite interesting if you were to pack the attention mechanism. Okay, because cosine similarity is something like attention. I mean, you actually do like U transpose T. So it's something like attention. Okay, and then if you were to use cosine similarity here, and then you just put like cosine over here. Oh, sorry, it's just U transpose T actually. U transpose T divided by U magnitude, V magnitude, because this will then give us the cosine between the two angles. So this cosine term is between 0 and -1 and 1. So this actually allows for negative weights in message passing. So this is the main feature. Just using this negative weights alone, you can see that actually it performs pretty well already. Okay, so my question that I have at the end as a discussion question is, how important is learning this Sheaf Laplacian? Is it just more work? Is it just more work on like a superficial inclusion of algebraic topology, or should we just focus on trying to generate these negative weights? Yeah, so that's a interesting thing for discussion. And yep, actually that's more or less it. Okay, for the today's topic on neural Sheaf diffusion. I hope I kind of exceeded a bit on my explanation, but I thought it's quite interesting. Yeah, so yeah, we can discuss a bit like, what do you think is the difference between Sheaf diffusion and attention, Sheaf diffusion and contrastive methods, and do we really need algebraic topology? All right, so yeah, I leave it to y'all to add your points if y'all have any. How do you find it? Or Jet or Duke, do you find any value in this Sheaf diffusion?
Oh, I think it's pretty interesting. Personally, I'm very new to graph neural network because I'm a math student, so I do research on optimization mostly. So I was doing a bit of topology and algebraic topology. So I see this and I find it's pretty interesting. I think yeah, you explained the concept quite clearly, but again, I feel like it's a complicated topic, and I also like a lot of, like, I guess, intuition with graph neural network. So I'll probably watch it again and yeah, read the slide again. But overall, I think you explain everything quite clearly. Yeah, thanks a lot.
Thanks, no worries. Actually, I'm not too sure whether what I say is fully correct because I'm also pretty new, but I would say that at least for the Sheaf diffusion part, I really feel like it's they're trying to use algebraic topology, but in the end is similar to like embedding space mapping. I mean, if you look at this thing here, it's like similar to just mapping an embedding space. If we just look at so
I can kind of get that part. Yeah.
I have my reservations whether this thing is needed, because you look at this empty set X finite intersection union. Can we just do away with topological space? I mean, why do we need it? I mean, you can just have, in the end, your topology space also just becomes H between the two sets, right? I mean, it's not really needed. I mean, what you can do is just do a mapping into the H. Yeah,
I think there's probably deeper reason why they choose this specific type of mapping. With I guess because topological spaces are very general. It can it's a very general type of space. Like if you have matrix spaces, and then you more generalize to topo, then I guess maybe there's a hidden reason. But yeah, like you said, I guess it can just be mapping, but I'm not sure. Maybe
actually,
there's a
they wanted to
motivation.
do it on continuous they want to do on continuous topological spaces and then discretize it only towards the end to edges and nodes.
Okay.
So initially they did continuous, but I think they realized because of this discretization process, in the end you also lose the information, or you can kind of overfit on the continuous case for topology. So in the end, I think what they did was they did everything in the discrete case. Yeah, so in the appendix, they actually did quite a lot of work on continuous space topologies. And they realized that the performance is not as good as the discrete case. So I would say that initially, I think they had bigger plans, but they had to scope it down because they didn't do too well.
Oh, yeah, that makes sense. Yeah.
Yeah, because if not, I don't see why we need topological space to just do this. I mean, if I don't tell you that this is topology, you will still get it, right?
The mapping and everything.
Yeah. I think one interesting thing which I haven't really found out fully is why must this H agree in the long run? Okay, so this one actually involves quite a bit of maths, okay, math, and I haven't quite understood why this H must agree in the long run. But the author said that if you were to do this Sheaf Laplacian, in the long run, it actually maps to the kernel space. So actually there's a slide on that. In the infinite time limit, this is just the projection into this kernel space. So this, I still haven't figured out the math behind this, but I just take their word for granted. I think this is very interesting if it really does do it, because then it really makes the framework very robust, because by making sure things align, okay, you can actually sort of express all the information in the graph very concisely, because all the information is passed to each of the other nodes. But because you set the H as the limiting factor, you make this a constant value. So the H will be like a sort of a constant value. You actually prevent mixing of the information, because in order for them to agree to a constant value, okay, you need to sort of have some form of polarization if it's different. And if it's the same, these two must be the same also. So this idea of agreeing onto a constant value through like common discourse space. So there's one way of doing this. These nodes can be called private opinion. Okay, and then like people can talk and share information. And then the middle part, the H here, can be viewed as like the public discourse space. Yeah, so I think this idea is quite interesting because, you know, I've been also quite interested in how neurons communicate with each other. And I have a feeling like the way we like sort of do like recognition or do decision making, we could have many neurons firing. Okay, each neuron could be a node. They fire, and then in the end, because they sort of agree on some public discourse space, you extrapolate this to more and more neurons. Each of these neurons will eventually get the right information, sort of through like voting or talking to each other. So I'm quite intrigued as to like why this actually works for this infinite time limit. Yeah, because this might actually give some insights about like maybe how consciousness is derived in the brain, how we get some information processed in the brain, because there's a lot of voting involved in the brain through the neurons. Yeah. Sorry, I'm just digressing a bit because I see some similarities between this and neurons in the brain. Yep. Okay, thanks, Duke. Yeah. Jet, you have anything else you want to add? Or Evan, you have anything else you want to add?
No, thanks so much for your sharing of this Sheaf Diffusion.
Okay, Evan, nothing else? Okay, if not, then I will just stop here then. Yeah. And next time around, we'll do the DeepMind one, where we will do the algorithmic alignment, like how to use GNNs for competitive programming. Yeah, so stay tuned for that one 2 weeks later. Yeah.